When you're ready, please.
Good morning, ladies and gentlemen. My name is Ibrahim from Brazilian team, and I'm going to present the problem number 7, drawing pins. First, the problem. The problem says, a drawing pin, for example, a thumbtack, floating on the surface of water near another floating object is subject to an attractive force. Investigate and explain the phenomena, and the problem asks, is it possible to achieve a repulse force by a similar mechanism? Okay, and here you can see the contents of my presentation. First, I'm going to talk about the theoretical introduction, then the experiments, and then the conclusion. First, I'll talk fast about the surface tension, which is a property of a fluid created by the interaction between the molecules on the surface. As you can see in this picture, it's defined by this expression, where delta P is the difference of pressure, gamma is the surface tension coefficient, and the R1 and R2 is the radius of the curvature. The surface tension tends to minimize the surface area of the fluid to minimize its energy. You can see a table for the surface tension coefficient for different fluids for a given temperature. Okay, the drag force. We have a body in movement inside the fluid, so we must have a drag force in this. We're going to have the flow. Okay, we're going to have the viscous force against the movement, and we are going to have the drag force given by this equation, where it's known but similar to the Stone's law, and we just put alpha with an adjusted coefficient. For this case, the literature says that we can approximate this coefficient for 1/2. Okay, R is the radius of the sphere, U is the absolute coefficient of the fluid, in this case Pascal times second, and alpha is the adjustment parameter, and dl dt is just the velocity. Okay, the capillarity is the interaction between the molecules of the particles and the molecules of the fluid. Okay, considering water as our fluid, we can have two kinds of interaction. When you have a hydrophilic object, it has affinity with the water. The force is going to be attractive between the molecules of the particle and the water. And the hydrophobic, the molecules of the particle is going to repel the molecules of the fluid. Here you can see a little animation for explaining these two cases. The hydrophilic particle is going to attract the water, and then the hydrophilic particle is going to repulse the molecules of the water. The main skills are just the curvature formed by the interaction between the molecules of the fluid and the particle. We can have these three basic kinds of interaction. Okay, the force is going to be attractive in the first two kinds and repulsive in the last one kind. The vertical force. Basically, the vertical force are the condition for the. If we have a particle more dense than the fluid, the vertical force are going to be the condition for the particle float. Okay. Considering a pin with a circular shape, in this case a semisphere, considering the Cartesian coordinates z and x, we're going to have the atmospheric pressure. The capillary force given by the surface tension tends to minimize the area in the deformation caused by the particle. We have the pressure force caused by the difference of the height in the fluid. We're going to have a buoyancy here. And the weight of the particle, of course. Considering theta c as being the contact angle between the fluid and the body, we're going to have these two forces, the capillary force and the pressure force, given by the following expression. When we solve this, we're going to have that Fp is just the buoyancy plus the capillary force. So we have the volume of the semisphere, and we have the area, the surface area in contact with the fluid. At the equilibrium, of course, we must have an equilibrium of force, and Fc plus Fp is going to be equals the weight of the particle. Okay, the horizontal force are the main force we need to study in this problem, because it's because the horizontal force that the two particles are in movement. Okay, considering a semisphere, of course, again we have a radius r. Considering an interface and a liquid fluid and a gas fluid, I'm sorry, it's changed, the gas is upper and the liquid is down, of course. We're going to have the contact point, and we can trace a tangent of the contact point, the red line. We have the contact angle, shown previously. And we have the tangent of the curvature of the meniscule. We are going to consider this angle as being theta. Okay, considering this height, we are going to have the tangent of this angle, the arctangent of this angle, I'm sorry. Okay, the interaction between the two particles are given by an approximation called Nichols superposition approximation, which is given by this expression, where BO is just the bond number, zeta1 and zeta2 are just two dimensionless parameters that I'm going to show later. K0 is a Bessel function of second kind in zero order, and LC is the capillary length given by this expression. We know that dl in this case is the force, okay, the differential of the energy in relation to the distance, okay. So in this we are gonna have the final equation where beta is just another simplification for the equation, okay. The dimensionless parameters I shown is the bond number, the first one, which is given by a very good approximation in this case, the r squared over the capillary length squared. The r is the radius of the curvature. K, in this case, zeta k, just denotes the particle number or the particle number 2. We have the d is the density of the particle divided by the density of the fluid, and theta c is the contact angle, and h is the height that I showed you. The case when the force is going to be attractive or repulsive. We're going to have attraction force when the force is going to be less than 0. So, till this occurs, we must have both sine of the angle less than 0, or both sines more than 0. For repulsive case, we are going to have one sign positive and another sign negative. Okay, the spacing function, the spacing function for small l is going to be given by the Bessel function for an asymptotic case in this case, because we don't have an analytical solution for the equation for bigger l. It's going to be given by, of course, the formula we shown you. The Bessel function is simplified for 1 over l, and using Torricelli's equation, we can get the l in function of the time. The experiment 1. The experiment 1, how you can see here. You can see in this move, I used 2 metal pins and they are attracting in water. Here you can see a picture of the experiment, and here you can see a graph of the position and function of the time for the 2 pins. You can see that they are equal, so the curvature of the meniscule are equal, and the graph is symmetrical. It's an experimental graph. Okay, here you can see a picture of the meniscule taken by the side of the beaker. Here you can see the length of the body, the angle of the meniscule theta, and the dimensionless parameter we have is b. Here you can see that we can get clearly the parameters of the experiment, the mass of the particle, and the surface tension coefficient for the water and air is given by it's given here, and the experiment was made in 20 degrees Celsius. Okay, the first experiment I'm gonna do with surfactant in the water, because it's gonna change the surface tension. Actually, it's gonna break the surface tension. Then the phenomenon doesn't occur. If the particle is more dense than the fluid, it's gonna fall out, and it's less dense. It's not gonna have attraction because we don't have surface tension. So if the surface tension term is gonna be 0, of course the force is gonna be 0. The third experiments, I made a table with the time of approach for different distance, in this case random distance, because we just need to see the pattern here. And actually you can see that we don't have a pattern, because in the water we have a kind of brown motion occurring in the fluid, and we cannot calculate it using any formula without statistical physics to calculate the time. So we can see here that the time is totally random. Okay. The 41, I can show you the repulsion, which the problem asks to create a similar mechanism with a repulsion. In this case, we can see that the curvature of the pin is gonna have a positive sign, and the curvature of the hydrophilic material, in this case, they are just a little piece of plastic. Okay, we have the repulsive force, how you can see clearly here. Okay, here you can see the graph of the repulse. The first time we give the impulse for the pin. Here you have when the pin stops, when it's close to the another object, in this case the hydrophilic object, and you can see that the shape of the graph is the same for both experiments. The precision of my experiments, it's given by the imprecision, sorry. It's given by the measure and the conversion, and here the graph for the two pins, the two objects. My conclusion, the movement is occurring by the Kepler force interaction between the two objects. The repulsion is possible if the sign of the angle 1 is positive and the other negative, or invert. The viscosity is important because it's going to make the graph just larger. We are going to increase the x. Okay? And the time of approach, we can see that for water, for example, we don't have a pattern because it's totally random, because a kind of brown emotion occurring in the molecules of the fluid and the interaction between the fluid and the particle. Here are my reference, and thank you for your attention.
Opposition and initial questions. Start with comments.
First of all, does the shape of the pin have any influence
Yes,
on
of
the
course.
phenomenon? And did you use spherical pins in your experiments, or like parts of spheres?
Just spherical pins, but it's not going to change the curvature of the meniscus. It's just going to change the vertical force.
Okay. And I was very intrigued by the fact that you had the height or the depth of the the depression measured to like 5 decimal places in millimeters. How did you measure this?
We took a picture of the side of the particle, and then we used a computer program, in this case CorelDRAW, to make the conversion.
So you were able to make such a sharp picture for such a small
We
thing?
took the picture close a room.
Yeah, with probably some special equipment, because in order to measure it properly, you have to be very close.
Yeah, of course, it's
Okay.
not so precision, but
I
the
was
only
just
thing we
interested
can
in
do.
precision was huge. Then I'd be interested in, could you, that's probably for the discussion, that will take a long time. My question is, did you try to measure the dependence of the position in time for attraction as well as for repulsion, like normal experiment, water, 2 pins attracting each other?
yes, I mean both.
Okay, thank you.
You're right.
And have you tried in any way to compare this experiment with your theory?
Yes.
And what did you get?
Of course, in this case, we can see that the Bessel function can be not solved analytically for the bigger distance.
Okay.
So we cannot have the function, but we compare it to the graphs.
Okay. And you didn't try to solve it numerically, did you?
Yeah, I have the values if you.
Okay. And did you try to figure out the shape of the meniscus for when there are 2 pins, not just 1?
Yes, in this case I made for 2 pins.
And is it symmetrical?
Yes, the graph, the first graph is symmetrical, the experiment.
Yeah, but was it for 2 pins?
For 2 pins.
Thank you.
Yeah.
Looking forward to the discussion. So, first of all, if I may ask you to go to slide 7 of your presentation.
The projector
Okay,
went on
maybe
standby.
while we're getting there.
projectable.
My question is, you had this measurement of the meniscus shape for 2 pins. How did you measure this? This is quite complex.
Okay, no, it's not so complex because I just have the beaker. Here I have the water, the curvature, and I took a picture from here.
Okay, and the picture wasn't distorted by the fact that the beaker is spherical, was it? Like curved?
Actually,
Yeah, but
because the distance is very small, so
Okay.
you don't have to distort.
okay, thank you. Next, could you know if the presentation is ready?
It's
Or-
not working, the
It's
projector.
not working.
Okay,
Oh,
we can talk like this if you want.
Yes, sure. Use that one, please.
Okay.
Okay, so meanwhile, I was interested in how your theory predicts stuff for spherical pins. Could you give me at least a qualitative explanation of how the shape could influence?
Actually, the phenomenon is going to be the same, but the shape can be changed, just the curvature of the meniscule and the pressure force. But the pressure force doesn't interfere in the attraction force, so it's not. There's no reason to say.
Okay, so now we've got the presentation. Slide
Okay.
7, please. Yeah, here we've got this picture.
Yeah.
Now, I'm wondering, there's a couple things which I'm not sure about in this picture. For instance, here, why do we have the pins above the surface of the water? Like the whole pin is above the surface.
Yeah, it's just an illustration.
Okay,
It's not proportional.
so it's not correct.
No, it's not proportional, it's just an illustration.
Yeah, so this doesn't happen in reality, right?
Okay, I just
Yeah.
I just need to compare hydrophobic and hydrophilic, not the curvature.
Okay.
Not the height.
Okay. Next, I'm interested in what happens if you have a hydrophilic object, but it's quite heavy. Its density is slightly higher than the density of water, and so it wants to go down. Can you draw the picture for me, please?
Oh, I didn't understand.
You've got an, now I can draw it because I want you to draw it. The point is, you've got an object which, if there were no surface tension, it would just go down because its density is slightly higher than that of the water. What will it do with the surface? What will happen? How will the surface look? If there's surface tension, for instance,
surface tension, so it just doesn't curl.
yeah, if you, I'm just, say you've got an object which wants to go, its density is slightly higher than water, but it's a very slight difference, the object is small, and so surface tension is actually holding it attached to the surface.
Okay,
But how will the
it's
shape
flowing,
of the...
but it's more dense than the fluid.
Yes,
Yes. Okay. What is important for us is just the curvature, so
yes.
it doesn't matter.
But I
Actually-
think it does actually, because if you've got, say this is the shape of the water, normally,
Okay.
like just, then we add the object. What happens is the object it doesn't want to float at the surface, it wants to go lower because its density is greater, but it is hydrophilic, and due to that the surface wants to stay attached to the object. So,
okay, if we... Okay, this kind.
yeah, sort of like
Okay.
that. Just to let the other people see. So here you've got a hydrophilic object.
Hydrophilic.
Yeah.
Okay, the curvature.
No, because you just said that, or I did actually, that the
Okay, but
object is heavier.
I haven't considered the weight of the part in this case. I just need to show the attraction between the molecules of the part and the
Okay.
molecules of the fluid.
But do you agree with me that if you have an object that is like more dense than the water and it's hydrophilic, so the surface wants to like stay attached to it, will it look like this, although it's hydrophilic?
I
got a
think you
spherical
changed hydrophilic with hydrophobic.
No, I did not. It's hydrophilic, therefore the
Okay.
surface is attaching to
If
it,
it's hydrophilic,
but it's
you will
heavy.
not break the surface tension scale.
I don't think so.
Okay.
Are pins hydrophilic or hydrophobic?
The pins are hydrophobic.
Hydrophobic. Have you tried using hydrophilic pins?
It's the same thing, like the plastic cups I use.
Okay, I don't agree with you that I think hydrophilic object will look like this if it's heavier, but that's all right. well, decent, but let's move on. My question is, in this problem you were supposed to investigate, so what did you learn about the relevant parameters? What are the parameters influencing this phenomenon?
The surface tension, the weight of the particle, the interaction between the particle and the fluid, and the shape of the meniscus, of course.
Okay. And as for the weight, how does the weight influence it? Now that you said that you didn't consider it?
Okay, the weight has influence on the vertical force.
Yes, and what does the vertical
What I
force?
study in this case is just the curvature. I don't care for the kind of object in this case.
Okay, I think you should
the angles of the meniscus.
Okay, let's look at the forces. Say you've got an object, you just have surface, and you put an object onto the surface. And now let's say that the force that the object's density is greater, so there's going to be some buoyant force acting on it, and some gravity force, which is bigger because of the density. So the object is going to move downwards, in my opinion.
Yes.
It's going to go down because of the difference in the forces. Now what happens, the surface is curved because the things are attached, and now you've got the surface tension with a vertical part which is holding it up. So this would be...
I don't agree, because if you have a hydrophobic material in this case, the water tends to be attracted by here, so it's going to break the surface tension and the body fell out.
Well, our experiments don't show that, but okay, let's say so. So then, can you please explain to me, physically, intuitively, why the objects attract or repel each other?
It's energetically favorable when you talk in terms of gravitational energy.
Correct.
You tend to minimize the area to minimize this energy.
But there's a lot of things. Okay, we've got this picture, and what happens here is that if this object, oops, sorry, I didn't know it was like, okay. What happens here? You've got an object which you say that the shape of the surface is like this. Yeah. Next, let's talk about hydrophobic. If the object is lighter than the water, will it still be energetically favorable for the object to stay down in the meniscus?
It still has a density lower than the water, but still have a weight, so
yes.
It's gonna curve the
but the water has a weight too.
Anyway.
But the water has a weight too. So
yes,
I think that energetically, for an object that is lighter than the water, it might be more favorable from the energetic point of view to go up the hill actually.
No, I don't think so, because it has a weight, it's not going to float on the water.
Yeah, but if there's a hole here that the object is taking, it's more energetically favorable for the water to be here because it's heavier. So the water should go here, and the object should be pushed uphill, shouldn't it?
Actually not, because it's not in direct contact with the water. If you look at this picture in a microscope, for example, you're going to see just the interaction between, electrical interaction between the molecules. But
yeah.
Direct interaction between the water and the...
Of course there's no direct interaction,
okay.
But the molecules are able to, like down below the surface, they're able to move freely.
But independent, it should be, has a weight bigger or less than the water, it's going to change the surface.
Okay, I don't agree with you, but let's move on. My question is, how did you calculate the shape of the meniscus for 2 pins?
The shape of the meniscus?
Yeah.
I bought a shape of the meniscus.
Yeah, but for the case when there are 2 pins.
The same thing.
The same thing, is it?
Yes, the 2 pins are equal.
Yeah, of course, but can you draw the picture for me, please?
Picture of what?
The meniscus shape for 2 pins. Okay. For instance, okay, so what you drew is that the pins are horizontal. Can you show me the videos?
Okay, of course.
Because I think that the pins were not, like when they moved closer to each other, they went this way.
Only when they are so close, I cannot study the movement in this case because I don't have the materials to do that.
Okay,
it's
so you didn't study that?
Case.
Okay, interesting. So I think that we were supposed to study the problem.
Any force when the distance tends to 0, we cannot study because it's actually the force tends to be infinite when the distance tends to be 0, and we know that.
That's of course that's the limit, but
okay, there's a limit because, of course, I said you in the presentation.
All right.
Here's the video if you.
Yeah, thank you. So what we can see here is that as the pins get closer to each other, yeah, thank you. They are kind of not being horizontal.
When they are so
here.
close,
Yeah, how close is it? If we could see it on the video, actually, does this work? No. Just to see when they are. Do you have a side view? No. Okay, it's pretty close. It's like 2 millimeters or 3 maybe.
Thank you very much.
But
You have
is it
1
time?
minute
Okay.
to summarize.
Thank you. So, I would like to conclude the discussion. First of all, I had a problem with the picture of a hydrophilic object, which has a higher density than water, or the other way around, a hydrophobic object with a density lower than the water. I do not agree with the presenter about the shape of the surface in this case. I also thought that the theory, there was some theory presented, but I don't think its potential was fully used. We did not see any predictions of the motion, which would kind of tell us how to confirm the theory. However, what we have seen was plenty of nice experiments which were performed quite well. We could see the repulsive force as the task stated. We could see the change of surface tension, and that the phenomenon did not work, so therefore it's a direct proof that surface tension indeed is very important in this phenomenon, and therefore I consider the experimental part to be fulfilled. However, I disagree with some aspects of the theory. Thank you very much for your attention.
I'd like to make some observations about the discussion. First of all, about the comparison between the experiment and theory, I made it qualitatively. So, about the predicted of the movement, yes, I predicted. I tell you of what occurs in all the cases. And about the precision, the conversion of the measurements of the meniscus, actually I took the measure of the height in centimeters. I'm sorry, in millimeters. So I just passed 2 meters. So we are gonna have more G. So it's inside the normal precision we have. About the hydrophilic and hydrophobic, I do believe that if you have a hydrophilic object more dense than the fluid, the water, because it's hydrophilic, the water tends to cover the object, so it's gonna sink. Okay. And about the shapes, the shape doesn't interfere in the curvature, in the shape of the meniscus. It's gonna interfere, can interfere about the angles in this case, but we studied that just the angles and not the cause of the angles. The discussion was very good, and that's all. Thank you.